Good morning class. Today we will discuss more about the molecular orbital theory. In case of molecular orbital theory, we discussed that when atomic orbitals are combining, there is formation of new type of orbitals that are molecular orbitals. Now, to explain the exact mechanism involved behind the formation of molecular orbitals, so for explaining molecular orbital formation, there is a topic given or there is a theory given which is called linear combination of atomic orbitals, which is in short called LCAO method also called. So, in case of linear combination of atomic orbitals, first we will see some introductory part and then we will apply and we will see how the molecular orbitals are formed. So, first of all, we must have heard about de Broglie's equation or de Broglie's theory, and de Broglie's theory states that an electron has a dual nature. Dual nature means double property, double character, and dual nature is that electron behaves as a wave, it behaves as a wave and also as a particle. It has dual nature, it behaves as a wave also and it behaves as a particle also. So, here in this case when we are discussing about formation of molecular orbitals, so in this case we will treat electron as a wave, and when we are treating electron as a wave, so we know that when a wave is travelling, so we are taking example of sine wave. This is a typical sine wave. So, we all know about waves. This is the origin part, this is crest portion or compression we can say, and this is the trough portion or we can say rarefaction. So, this part which is part of crest or compression, this is represented by plus, I have represented it by plus, and the portion of trough or rarefaction is represented by minus. So, when we are discussing about atomic orbitals and molecular orbitals are formed by the overlapping of atomic orbitals, and atomic orbitals are containing unpaired electrons. So, if the overlapping is taking place between atomic orbitals, it is possible that the crest of one overlaps with the crest of second, or it may be possible that trough of first overlaps with the trough of second, or it is also possible that crest of first overlaps with the trough of second, or trough of first overlaps with the crest of second. So, if there is overlapping of crest of the two atomic orbitals or trough of the two overlapping atomic orbitals, then this type of overlapping is called phase overlapping, and as a result of phase overlapping, bonding molecular orbitals are formed. But if the crest of one or the trough of second or the trough of one or the crest of second overlaps, then this type of overlapping is called not in phase overlapping, and as a result antibonding molecular orbitals are formed. These bonding molecular orbitals are stable because their energy content is low, they have a low energy content, but the antibonding molecular orbitals are not stable or they are less stable because they have a higher energy content, and we have already discussed in case of chemical bonding that higher the energy content, lower will be the stability. So, this is all about the formation of phase overlapping, not in phase overlapping. So, again let us see what is phase and not in phase overlapping. So, if there is a phase overlapping, means the crest of both the atomic orbitals or the trough of both the atomic orbitals overlap, and this if overlapping is taking place between two crest or two trough, then this is called phase overlapping, and in case of phase overlapping, bonding molecular orbitals are formed which are stable due to less energy content. But if the overlapping is taking place as crest of first and the trough of second, or the trough of first and the crest of second, then this type of overlapping is called not in phase overlapping, and as a result of non in phase overlapping, antibonding molecular orbitals are formed, and these antibonding molecular orbitals are less stable because they have a higher energy content. So, let us discuss briefly about these two types of molecular orbitals. So, let us first discuss about bonding molecular orbitals. So, let us first discuss about bonding molecular orbitals. So, some of the features we have already seen, some we will discuss. So, first point is it is formed by phase overlapping. When there is a phase overlapping between two atomic orbitals, it results in the formation of bonding molecular orbital. Second point, that it is stable due to less energy content, or due to less energy it is more stable. And the third and the most important point is that its representation in the form of wave equation or wave state, that is in the form of psi. So, we must have heard about this word, it is called psi, and this is called wave function, or it is called wave state. So, this psi is a function, it is a tool which is called a wave function or wave state. It means that if an electron is moving in the form of a wave, then its position, its displacement, its all characters can be represented by a symbol, a tool, a function which is called psi, and it is called wave function or wave state. So, the complete motion of electron in the form of wave can be represented by this psi. So, if we represent this psi, so we are representing for bonding molecular orbital. So, we have for each and every wave, we have a wave function, that is psi. So, since we are representing for bonding, so we are writing psi b, means bonding molecular orbital, and if this bonding molecular orbital is formed by overlapping of two atomic orbitals, then both of them will have their separate wave functions. So, let us treat one as psi a, where psi is first atomic orbital, combining atomic orbital, and the next one is psi b, where b is the next atomic orbital, which is having phase overlapping for the formation of bonding molecular orbital. So, this is the equation, in the form of wave function which represents the motion of electron in bonding molecular orbital, where this psi b represents wave function for bonding molecular orbital. This psi a represents wave function for combining atomic orbital a, we are treating it as a wave, so we are saying it is A, and this is wave function for next combining atomic orbital, which is our B. So, this is the equation in the form of wave form, which represents that if a bonding molecular orbital is formed, then the electron which is formed, with the electron which has having bonding molecular orbital, which is forming bonding molecular orbital, then this will be equal to the summation of both the wave function of the combining atomic orbitals. So, we are writing psi b is equal to psi a plus psi b. Now, we will introduce one more term in this concept, and that is the psi square term. So, earlier here we have written the equation in the form of wave function, that is psi b is equal to psi a plus psi b, Now we will introduce one more term, that is called psi square, and this psi square represents charge density. It represents charge density. So it shows that if a wave is moving, if an electron is moving in the form of wave, then at a particular location, at a particular point, what is the distribution of charge? What is the density of charge? And that distribution of charge is represented by psi square, which is called charge density. So in the similar manner, we will derive the charge density for this bonding molecular orbital. So when we will derive the charge density for this bonding molecular orbital, it will be equal to psi b square, and it will be nothing but the whole square of this entire term. So it will be equal to psi a square plus psi b square plus 2 psi a psi b. This is the next equation which represents the charge density of this bonding molecular orbital. So this was for explanation. So this is our first equation which we derived for bonding molecular orbital, and this is the second equation which we derived for anti-bonding molecular orbital. Bonding molecular orbital. So in this case, this is our bonding molecular orbital. Let us see what are the major points of bonding molecular orbital. In case of bonding molecular orbital, it is formed by phase overlapping. It is stable due to less energy content. And the third point is, we are representing the motion of electron by a quantity, by a tool which is called wave function or wave state, wherein we say psi b is equal to psi a plus psi b, where this psi small b represents wave function for bonding molecular orbital. Psi a is the wave function for the combining atomic orbital. If it is a, then it will be psi a, and the psi b is the wave function for the next combining atomic orbital, and we are treating it as b. So it will be psi b. Now we are introducing another term which is called psi square, and it is nothing but the charge density. So if we write the charge density equation for this form, then it would be the summation of whole square of the above equation. So it would be psi b square is equal to psi a square plus psi b square plus 2 psi a psi b. So this is the complete information, this is the complete characteristic features of bonding molecular orbital. Now let us see what are the characteristic features of anti-bonding molecular orbital. Anti-bonding molecular orbital. Now, in case of anti-bonding molecular orbital, it is formed by not in phase overlapping, when there is not in phase overlapping. Second point, it is less stable due to more energy, because they have higher energy content, they are less stable. And the third point is that its equation in the form of wave function. Then if we write a wave function for anti-bonding, psi a represents wave function for anti-bonding molecular orbital, then it would be equal to the difference in wave functions of the two combining waves. So psi a is the wave function for anti-bonding molecular orbital. This is the wave function for the first wave A, which is, we are treating atomic orbitals to be like a wave because they also contain electron. So wave function for the first combining atomic orbital, let it be A, and this is the wave function for the next combining atomic orbital, let it be B. And if we write the charge density, so we are writing the equation once again, psi A is equal to psi A minus psi B. This is the first equation for antibonding molecular orbital. And when we will derive the equation for charge density, it would be square, and again the whole square of this form. So, it would be psi A square plus psi B square minus 2 psi A psi B. So, this is the next equation for the charge density of antibonding molecular orbitals. So, these are some of the features of antibonding molecular orbitals. They are formed by not in phase overlapping, less stable due to more energy content, and if we write the equation in the form of wave equation for antibonding molecular orbitals, then it would be psi A is equal to psi A minus psi B, where the psi A is the wave function for the antibonding molecular orbital. A represents antibonding. This psi A, capital A, it represents the wave function for the first combining atomic orbital, let it be capital A, and this is the wave function for the second atomic orbital, let it be B. And when we will derive the charge density, this is the charge density for the antibonding molecular orbital. So, when we will derive the equation for charge density, it would be equal to the whole square of this difference. So, it will be equal to psi A square plus psi B square minus 2 psi A psi B. So, thank you class.